Hello students, myself Somiya SP, Assistant Professor, Department of Civil Engineering. In this video, I am presenting the Module 3 of Design of Hydraulic Structures. In Module 3, it deals with, first one, it is the cross drainage work, which can be an aqueduct or a siphon aqueduct. Next, it is the canal fault with a trapezoidal notch. Third is the Sarda fault with high discharge only. Next is the siphon well drop, and last one is the cross regulator. So actually 6 design and drawing is being discussed in module 3. But in this slide we will be discussing about the cross drainage work, that is the aqueduct. In aqueduct or in siphon aqueduct, we have to first identify the type of cross drainage work, whether it is an aqueduct or a siphon aqueduct. So how can we analyze it is an aqueduct or a siphon aqueduct? That is, from the figure, for an aqueduct, canal bed level will be above the FSL of drainage. But in the case of siphon aqueduct, canal bed level will be below the drainage FSL. That is, in aqueduct and siphon aqueduct, canal is above the drain. But due to the difference in the bed level of the canal and drainage FSL, it has been divided into aqueduct and siphon aqueduct. That is, in the case of an aqueduct, canal bed level will be above the drainage FSL. But in the case of siphon aqueduct, drainage FSL will be above the canal bed level. So from the question, canal bed level and drainage FSL, we can identify which is the cross drainage work, that is whether it is an aqueduct or a siphon aqueduct. Next up, it is the calculation of maximum flood discharge. Normally the questions will be given with the flood discharge, but in some cases it will be provided with a constant and an area. So two formulas can be applied based upon the constant given. If it is a Dickens constant, we apply the Dickens formula, and if it is a Rayas constant, we apply the Rayas formula. That is, for a Dickens formula, QD is equal to, that is the discharge, is equal to CD into A raised to 3 by 4. That is, CD is the Dickens constant and A is the area. Whereas in Rayas formula, QR, discharge, is equal to Rayas constant into area raised to 2 by 3. Next is the fixation of waterway, that is the fixation of canal waterway. That is by Lacey's theory, that is P, vector perimeter P is equal to 4.75 root Q. In length of the waterway, P is equal to L. So L will be equal to 4.75 root Q. Next, we have to provide piers and span, so that we assume a certain value for a pier and a span. That is, provide a span width of 9 meter and a pier width of 1.5 meter. So we have to find how many bays should be provided within the length of waterway. That is, bays will be equal to length of the waterway divided by span width plus pier width. That is, will be equal to P by 1.5 plus 9. So we get the number of bays. Next, we have to find out what is the number of piers. That is, base minus 1 will give the piers. Why? Because in two end projections, we will be providing with the wing walls other than the piers. Hence, base minus 1 gives the number of piers. Next step is to provide the clearance and the freeboard. Now, what is a clearance? Clearance means the distance between the canal bed level and HFL. For an aqueduct, clearance should be provided, but in the case of a siphon, whether the HFL is above canal bed level, we have to provide zero, that is zero clearance. So in the case of an aqueduct, we have to provide clearance. What is a clearance means? Clearance is the distance between bed width of the canal and the HFL. Next is the freeboard. What do you mean by freeboard? Freeboard is the distance above canal FSL. Next is the length of contraction and expansion transition. Now you should provide, this is the figure, that is, we will be having a waterway length with a flumed bed width, that is reduced bed width. Normally a structure that is being constructed in the water, we will reduce the water width, that is the flumed bed width. Actually original bed width will be taken as normal bed width, and normal bed width half will be taken as the flumed bed width. That is, flumed bed width will be equal to half of canal bed width. Next, we have to find out the contraction transition CT and expansion transition ET. So that we have to provide a slope. In contraction transition or a CT, we provide a splay with 2:1. Whereas in expansion transition or ET, we provide a splay with 3:1. So the length of contraction transition CT is equal to original bed width minus flumed bed width divided by 2 into splay. Similarly, expansion transition is also equal to original bed width minus flumed bed width by 2 into splay. The difference between contraction transition and expansion transition is the given values for the splay, that is 2/1 and 3/1. Next step is to find out the calculation of bed level, water surface level at various sections. So here the original bed width, the flumed bed width will be divided into as 4 sections. That is section 1:1, section 2:2, section 3:3 and section 4:4. Then we have to find out the water level, the bed level and the total energy level at each section. So first we begin with the section 4:4, then section 3:3, then section 2:2 and finally section 1:1. So at section 4:4 we start with the bottom level, that is the bed level of the canal. That will be given in a question. So bed level at section 4:4 will be given in question. We have to write out the answer. Next, we'll move on to the reduced level of water level. Reduced level of water level will be equal to bed level plus depth of the water. Next, what is the total energy level? That will be equal to water level plus V4 square by 2G. Now, how to find the velocity? That is velocity from the continuity equation, that is Q by A, where Q is the canal discharge and area is equal to B plus ZY into Y, where B is the bed width, Z is the slope and Y is the depth of water. Next, we move on to the step number 2, that is considering section 3:3. From section 3:3 to 4:4, that is from the flumed bed width to the normal bed width, it is an expansion. So there will be losses due to expansion and a frictional loss. But frictional loss is negligibly small, so we neglect that and we only consider the loss due to expansion. Now, how to find the loss due to expansion? That is equal to 0.3 into velocity at 3, that is V3 square minus V4 square by 2G. Now, how to find the velocity V3? Velocity will be equal to Q by A, where Q is the canal discharge and area at section 3:3, which is a rectangular section. So, flumed bed width into depth of water will get the area. In section 4:4, we find out the values from the bottom, that is bed level, water level and total energy level. But in the other cases except section 4:4, that is 3:3, 2:2 and 1:1, we find out from the top to bottom. That is, first we have to find out the total energy level, then the water level and the bed level. So we have to find out what is the reduced level of total energy level at section 3:3. That is equal to reduced level of total energy level at section 4:4 plus loss. Next, we have to find out the water level. Water level is equal to reduced level of TEL at section 3:3 minus V3 square by 2G. Next, we have to find out the bed level. That is equal to water surface at section 3:3 minus depth of the water. Next, we move on to the section 2:2, which is in a rectangular portion, that is the flumed bed width portion. There only friction loss, because from section 2:2 to section 3:3 it is a flumed bed width. There is no expansion, neither contraction. So only the friction loss. Friction loss is find out from the Manning's equation, that is Q is equal to 1 by N into A square R raised to 2 by 3 S raised to half. Now frictional loss is equal to HL is equal to Q square ln square divided by a square r raised to 4 by 3. Similar as that of the section 3.3, in section 2.2 also we find out from the top level to bottom. So first we will be considering about the total energy level at section 2.2 is equal to total energy level at section 3.3 plus the friction loss. Next is the water level. Water level at section 2.2 will be equal to reduced level of TEL at section 2.2 minus V2 square by 2G. Next about the bed level. That is bed level is equal to water surface at section 2.2 minus depth of the water. Next at section 1.1, which is our last section. So from section 1.1 to section 2.2, that is normal canal bed width is reduced to the flumed bed width. So actually it is a contraction. So there will be a loss due to contraction. That is equal to 0.2 into V1 square minus V2 square by 2G. Similar in the case that of the section 3.3 and 2.2, here also we have to find out from the top level to the bottom. That is total energy level at section 1.1 will be calculated first, and then the water level, and then the bed level. Similar as that of section 3.3 and 2.2, the equation is same. That is reduced level of TEL at section 1.1 will be equal to reduced level of TEL at section 2.2 plus loss. Next about the water level at section 1.1 will be equal to reduced level of TEL at section 1.1 minus V1 square by 2G. Next is the calculation of bed level, that is equal to water level at section 1.1 minus depth of the water. So we get all the total energy level, water level and bed level at 4 sections. We have to mark the total energy level, water level and the bed level for the 4 section as given in the figure. In total energy level, we get the nearly a straight line. In water level also nearly straight line, but in the case of bed level, we get the actual trapezoidal section. Next step is the design of transition, that is CT and ET, contraction transition and expansion transition. Here we have two equations, that is Mitra's hyperbolic equation and Chaturvedi's semi-cubic parabolic equation. Normally we adopt the Mitra's hyperbolic equation, which is nearly simple. And in case of a question, if it is represented as use Chaturvedi's equation, we have to use the second one. Now, what is its data we'll be looking? That is, BC is the original canal bed width, BF is the flumed bed width, BX is the bed width at the section X distance from the section 2.2 to section 1.1 in the case of a contraction transition. But in the case of an expansion transition, X is taken as X is a distance from the section 3.3 to section 4.4. That is from the flumed bed width to the original canal section. Now LF is the length of the flumed portion. Now the Mitra's hyperbolic equation, Bx is equal to BC into BF into LF divided by BC LF minus BC minus BF into X. Actually, the LF is being divided into certain intervals, that is the X value, and we substitute the X values in Mitra's hyperbolic equation where the original canal bed width, flumed bed width and length of the fluming section is known. Hence, we find out for a different X values, we get different Bx value. But in the case of Chaturvedi's semi-cubic parabolic equation, just opposite of Mitra's hyperbolic equation. That is, we just divide the bed width as different intervals and we find out the X values. That is, X is equal to LF into BC raised to 3 by 2 divided by BC raised to 3 by 2 into BF raised to 3 by 2, the whole into 1 minus BF by BX, the whole raised to 3 by 2. Next, the last step of the aqueduct, that is design of a canal trough. I repeat, it is the last step of the aqueduct, which is a part of cross drainage work. That is design of a canal trough. That is just a sentence, that is canal trough is divided into two compartments. We have to mention the dimensions of each compartment and is being separated by an intermediate wall with 0.3 meter thickness. Next point, inspection route shall be provided on the left bank. And outer wall and bottom slab is provided with a thickness of 0.4 meter. Next, if needed, we can provide that is clearance of 0.5 meter and freeboard of 900 mm is provided. Finally, we just draw a figure with the rough data, that is zero point 0.4 outer wall thickness, zero point 0.4 base slab thickness, 0.3 meter an intermediate wall. On left hand side it is an inspection road, FSL of a canal and the two compartments, canal's bed level, drainage FSL which is below the canal bed level, and the finally bed level of a drain. Thank you.